Thanks. I'd like to invite our AV team to kindly launch the live stream. Great. On behalf of the New York Academy of Sciences, I'd like to once again welcome our remote audience for the 13th Annual Machine Learning Symposium. And I'd like you to join me in welcome our third keynote speaker, Ruslan Salakhutdinov, sorry. Russ is a professor of computer science in the machine learning department at Carnegie Mellon University and director of AI research at Apple. His interests include deep learning, probabilistic graphical models, and large-scale optimization. He received his PhD from the University of Toronto and spent 2 years as a postdoc at the MIT Artificial Intelligence Lab. He was an assistant professor at the University of Toronto, and he's been the recipient of many awards and fellowships. And today, if he hasn't changed his talk title since he submitted it, I don't think he has, he'll speak to us on integrating domain knowledge into deep learning. So please welcome Russ. And I apologize for butchering your last name.
All right, so I think, all right, that works. Great. Well, thank you very much for the invitation. It's fantastic to be here. What I'd like to do today is I'd like to talk to you about a particular topic that I've become interested in just the last year or so. So apologies for some parts of the talk are a little bit terse, but I'm going to talk about how can we integrate some of the domain knowledge into deep learning models. Okay. And as you know, the impact of deep learning has been, quite substantial. If you look at speech recognition, vision, language understanding, there's a lot of work happening in the space of drug discovery, medical image analysis, and health and such. So that's all good. And sometimes, when you hear talks on deep learning, typically people show these examples where, as you increase the data size, you make your models be bigger, the accuracy of these models increases and so forth. So typically, these models work well when you have lots and lots of data, particularly labeled data, right? And this is where these models really shine. What I'd like to talk to you about today is, how can we integrate domain knowledge into these models? And if you think about some of the key ingredients of the statistical machine learning systems, and deep learning is a statistical ML, not surprisingly, we typically think about, some kind of model architecture, or think about model class. That's one way of maybe integrating some kind of prior knowledge. Or maybe perhaps we can think about learning algorithms, right? How we do learning from data. Maybe there we can integrate some domain knowledge. And again, the real question is how do we, put domain knowledge into either one of those key ingredients? And so what I'd like to talk to you about today is consider three classes of domain knowledge. We're going to look at the relational domain. We're going to look at the logical, how can we incorporate logical knowledge into these models. And there's a third one, which is a scientific knowledge, which I'm not going to talk about today, but I think it's a very important and very sort of active area of research. So if I think about relational knowledge, right, we typically think about having some entities and defining some relationship between these entities, like Bob is the father of Alice. And this can be available to us from relational databases and knowledge graphs, right? And there's been a lot of work in that space. A lot of it is grounded in graphical models, probabilistic graphical models, right? You think about probabilistic relational models, relational dependency networks. There's a huge body of work of incorporating that domain knowledge into graphical models. There is also a lot of work in the embedding space. So for example, here we're going to be representing entities or certain data points as vectors in some vector space. Right? And we're going to be learning these representations by predicting an entity given its context. So for example, very popular latest developments in natural language understanding are these models based on, these embeddings based on BERT and Elmo, and some of you might have heard about those. They really, work surprisingly well, and surprisingly well across a whole bunch of NLP tasks. And so what I'm going to show you is I'm going to show you how can we incorporate these models in deep learning models, particularly using what's called graph propagation. Logical knowledge is also an important class of models. Think about propositional or first-order logic. So here, for example, instead of just giving you a relationship between entities, I can say, well, if an object has a wing, it has a beak, it must be a bird, right? So how do we incorporate that kind of structure into these models? And again, there's a lot of prior work. You know, if we look at the Bayesian networks from Horn clauses, probabilistic context-free grammars, Markov logic networks, and such. And what I'm going to show you is how can we incorporate that type of information or general classes of constraints into deep learning via so-called distillation framework. And I'll make it more precise as I go through the talk. And obviously, there is also scientific knowledge. I think it's also, you know, a really important part of how we can use that knowledge. You know, think about Newton's laws of motion, right? Think about conservation laws of principles, invariances. Maybe we can be learning PDEs from data, you know, regularizing dynamical systems and so forth. So there's a little bit of work happening in that space, but not as much as it should be. Now, let me motivate perhaps how we're going to try to do that through a few examples. I'm going to be focusing primarily on examples that are based on natural language understanding, right? There's a class of, you know, fascinating work that's been happening in the last 5 years or so called reading comprehension tasks. Imagine that I give you some context. These are, I guess these were coming from news articles, CNN news articles. And imagine I give you some context. And it says, arrested Illinois Governor Rob Blagojevich and his chief of staff, John Harris, on corruption charges. And this goes on and on about what's been happening. And I think you remember back in 2008, there was this big scandal of Rob Blagojevich basically trying to sell President-elect Obama's seat in the Senate, right? And I give you a query, right? And you have to, and if you have to tell me who's X, right? To us, it's obvious that it's Rob Blagojevich, but there are other things, you know, that you can see in the context. You can see John Harris, you can see Barack Obama. So who is that? And it turns out to be quite challenging to answer those questions, right? These are natural form, natural language form, right? And obviously the answer is Rob Blagojevich. So the basic algorithms underlying a lot of the work in sequential processing are models based on so-called recurrent neural networks. And the key idea behind these models is that you can think of them as you have some hidden state representation at time t-1. You have some hidden, you have some input at time t. You think of it as a word in the sequence and such. You have some nonlinearity, and then that produces the next hidden state, right? If phi here is linear, it would be akin to linear dynamical system, for example, right? So classes of HMMs and linear dynamical systems are special cases of these kinds of models. And there are a whole bunch of them, you know, based on recurrent, like something's called GRUs and LSTMs, long-term, short-term memory networks and such. And so what we can do in these kinds of models, the basic architectures that have been very successful are using these recurrent networks to encode some representation of sentences and queries. And then what you're going to be doing is you're going to be using so-called element-wise multiplication to model interactions between documents and query. And it turns out that sometimes people call this attention. It turns out to be quite an important architectural structure that you encode into these models. Essentially, it's telling you, you know, if you see Obama or if you see Prague here and you see Prague here, maybe there's a context should be similar. So maybe you should be paying more attention to what's happening around these tokens. And if you look at these entire architectures, they're becoming more and more complex, right? Many of you have probably seen, you know, through some of these talks, you have linear systems, so you have convolutional neural networks. These kinds of models, you can think of them as recurrent networks stacked on top of each other, and they're becoming fairly sophisticated. You have these gating mechanisms, these attention mechanisms happening at each layer, and then you're trying to come up with an answer, right? So these models becoming more complex as we're building them. And it's surprisingly, you know, you see some interesting phenomena coming out of these models. So for example, if you look at the first layer, and if you look at what the first layer is paying attention to, it's basically associating alleged corruption with Rob Blagojevich. And the second layer sort of starts associating Senate seat with Rob Blagojevich. It kind of picks up on these salient features that Senate seat and corruption are associated with Rob Blagojevich, so maybe the answer should be Rob Blagojevich, right? It's a very basic form, I don't want to call it reasoning, but basic form of, oh, sorry. There you go. Apologies. But the big question is, how do you incorporate knowledge? Maybe we can use core references, maybe you can use entity relations, maybe you can use word relations to really get to a better representation, right? So one way of doing this is by introducing perhaps different types of architecture. So imagine that I give you these 3 sentences. Mary got the football, she went to the kitchen, she left the ball there. If I ask you the question, where is the ball? To us, it's kind of obvious, right? It's in the kitchen. But you have to do some form of reasoning to figure out that the Mary and she, that means the same thing, and the ball is in the kitchen and such. You can do it using recurrent networks, but it turns out it's very hard to capture long-term dependencies. You can use co-references, for example, so you can augment your model with these additional links. You can maybe put some price by basically saying ball and football, they mean the same thing. And it turns out you can construct similar architectures, in this case these are recurrent neural networks, but that have that particular structure embedded into these models. And it turns out that can give us some additional gains. And now if you look at the space today, there's something called attention or transformers, which is effectively doing something quite similar, but you're essentially linking everything to everything. Now, let me look at one specific way of trying to incorporate relational knowledge. We've been looking at this problem of open domain question answering systems, right? So the questions here is that, can you find answers to factual questions that are posed in natural language? And that's obviously it has big application domains, and pretty much, whenever you're using your personal assistant, you're asking a question like this: who voiced Meg in Family Guy? You want to be able to come up with 2 answers. And then maybe if I ask you who first voiced Meg in the Family Guy, you want to come up with another answer, right? So these things, can be quite complex depending what your question is. And traditionally, if you actually look at what's going on in industry, and presumably what actually works, is using so-called knowledge bases, right? I'm constructing this explicit representation of who's related to whom, who's the actor in what movie, and so forth, and I'm building this gigantic knowledge graph. And then if I ask you the question, who first voiced Meg in Family Guy, I have to do something called semantic parsing, which means that I have to identify that Family Guy is a show, right, and Meg is a character in that show, so I can map it into my knowledge graph. And it turns out that that process is extremely difficult, and when you talk to your personal assistants and it gives you a junk answer, basically it fails to do that most of the time, right? But more recently, as I mentioned before, with these reading comprehension tasks, people are noticing that we can now get these neural networks to work better and better. So here I'm just using unstructured text, Wikipedia articles. Maybe I retrieve the top 10 choices or 20 choices, and then I do this complex deep learning type of a model to answer the question, right? And these models are beginning to work surprisingly well, but they're not as good so far as these knowledge graph type models. And so what we've been trying to do is we've been trying to say, well, can we combine both of these representations, right? So we can have some representation of the knowledge graph. We can have some representation of unstructured text, like text in the Wikipedia. And then what we can do is we can pass information back and forth between these 2 sources of data, right? And let me tell you how we can do that. The first thing that we need to do is we need to understand the graph structure of the knowledge base. And how do we read from graphs? So given some graph with vertices and edges, vertices representing entities, edges are representing some relationship between these entities, and we have a natural language question queue, we basically want to be able to learn a function y such that it takes value 1 if and only if that particular entity answers our question, okay? And what we can do is we can basically say, well, there's a softmax representation, and where HQ can be representation of a sentence that's coming from a neural network or some, typically it's an LSTM or a transformer type of a network, and HV is the node representation coming from what's called the graph convolutional network. So there are 2 pieces that I want to emphasize is that when we're working with graph, there's a beautiful work on using graph convolutions. And I think this is, so far, is a very underappreciated area of research on how we can actually learn structures from graphs. And it's actually quite simple. We're basically saying, well, if we're doing some kind of reasoning or some kind of propagation on the graphs, we're basically initializing these edges, these vertices to some values. And then if we want to update this node, we essentially just go through the same process as what we've been doing with recurrent networks, right? We're just taking the graph structure into account. And there's been some work on actually looking at the relational graph convolutional networks where edges represent different relations and different types, and we can learn these parameters as well as we're doing propagation on graphs. So we can represent entities. We can also look at unstructured text, such as documents, right? And then what we can do is we can propagate information from the entities to the documents. And that gives us much better context, and it allows us to learn much better representation. When we talk about McGriffin and its representation, it's coming from the knowledge graph, that can impact our representation of the text that we're constructing, right? And the other way around, the representations that we're getting from the text can be propagated to the entities as well. So there are two things that we're doing here. We're trying to use knowledge graph and relational information to enhance our representation that we're getting from the text. On the other hand, what we're also doing is we're getting representation from the text and propagating that information into the knowledge graph itself. So potentially that could help us construct better representations or construct less noisy representation of the knowledge graphs, right? Because one of the big problems with the knowledge graphs, as far as we see in the real world, is knowledge graphs are noisy and they're missing, and sometimes you can't really answer questions just based on the knowledge graphs themselves. So there's some active work that we're trying to come up with these hybrid models, and our initial results do show that we can improve over, many of the existing state-of-the-art techniques, but that, again, we're still trying to figure out exactly how that should be done. Okay? Now, let me spend a little bit of time talking about, we've talked about relational structures. How can we incorporate logical information or perhaps constraints into our models? So imagine that I have some statistical model. You can think of it as, let's say, as a generative model, or maybe you can think of it as, a classification model. This is what we have here. And let's say I give you some function f, right? And this function f could be a neural network. It's going to be parameterized by some parameters phi. And I'm going to be defining these functions in such a way that high values of phi basically allow me to encode some knowledge about x, right? So the higher the value, the better x is with respect to the particular knowledge that I want to encode into my model. Okay? So think about logical rules. If the logical rules is 1, then it's satisfied. If it's 0, then it's not satisfied, right? Here's an example. This is a particular example that people use in computer vision domain. Imagine that I give you source image, and I give you the target pose. And this is, you can think of these as key points. And what I want to do is I want to take the target pose. I want to take my generative model. It could be explicit generative model, it could be implicit generative model, like a GAN, for example, generative adversarial network, and I want to be able to generate that image such that it corresponds to the true target. Okay? So that's a well-defined problem. I can train that, but maybe what I want to do is I want to enforce some additional constraints on what I'm actually generating, right? Maybe I want to put some kind of constraints by saying the parts, the body parts, from what I'm generating should be matching to the body parts of the true image, right? As an example of what the constraint could be. So how do we make sure that these constraints get embedded into our models when we're generating them? Right? And even better, can we actually define a learnable module that can adapt to our algorithm or can adapt to our model here such that we can, we can satisfy this structural consistency. Okay? So the question is, how can we do that? It's another way of incorporating perhaps constraints into your model. Here's another example that we worked with on sentiment prediction, right? Suppose in sentiment prediction, I give you a sentence, and sentence of the form, this was a terrific movie, but the director could have done better, right? Now, the sentiment of, I would argue, the sentiment of this sentence is negative, right? Even though I do say things like this was a terrific movie. And the reason why I say it's negative is because this kind of interesting structure that you see in a sentence, right? So typically, you can come up with some rules by saying, well, if you have a structure A but B, then you basically want to just get the sentiment of B. The sentiment of B should be dominating, right? So now the question is, if I'm a deep learning person, I could say, well, I'm just going to learn it from data, right? And that's true. Maybe with enough examples, you can learn it from data. The question is, if I give you these rules, can you somehow force your network to perhaps abide by these rules, right? Or at least initially. So how can we do that? So one way to, it turns out, one way to impose the constraints is to try to maximize, is to try to regularize the model and is to try to maximize this expectation. And this expectation with respect to your model P, this expectation is very intuitive, right? It's basically saying assign high probability to the regions of the input space where this constraint is satisfied, right? So when I'm generating an image, I want to sort of generate image mostly in the space where this constraint is satisfied, right? So that's sort of a high-level idea. And then I can maybe maximize my objective. So my loss here could be a typical regular loss. What I'm trying to do could be log loss, cross-entropy loss, whatever is it that you're trying to optimize. And this is more like a regularization that you're imposing on your model. And it turns out in many cases, if you have a complex model P, like a generative model, it's difficult to compute in many cases. It's difficult to satisfy those constraints. So what can we do here, right? If it's easy, if it's a simple model, yes, I can do that. And it turns out there's a beautiful work on posterior regularization. I think people sort of forgotten a little bit, particularly in the deep learning community. That was done back in 2010. It seems like in our community, we sort of reinvent the wheel. You know, we go back 10 years and figure out what people have done and then reinvent it. But there's this beautiful framework that basically says the following, okay? It says, can I introduce the variational distribution Q? So can I find another distribution Q such that, you know, perhaps it's easy to compute, but such that it's also close to P, to my original distribution P that I'm trying to model, right? And essentially, pretty much all of the variation learning sort of does something as such. It's basically saying, well, if it's hard for me to compute this expectation, maybe what I can do is I can try to compute this expectation with respect to Q, right? And what I'm going to do is I'm going to actually try to force my Q distribution to be close to P in terms of KL divergence. And that's pretty much, if you look at variational learning, that's all we do. We basically say, well, there must be some other distribution Q that I can deal with and try to make it as close as possible to P as possible, right? And so now I can form this objective, right? So I can form the objective when I'm minimizing with respect to the parameters of my model and also with respect to this variational distribution Q. And it turns out for this particular formulation, there is an optimal solution for Q because KL is convex and we can just find the optimal solution. And the optimal solution has an interesting form, right? It has that particular form. Intuitively, what this form is doing is essentially saying that high values of my constraints, right, should result in higher probability on the Q. So if this is my model, right, if I'm in the space where this constraint has high values, I'm essentially increasing the probability of X on the Q. If it has low values, I'm effectively decreasing the probability on the Q, right? So I'm taking my model P and just basically saying, you know, if it satisfies my constraints, make it more probable. If I'm not, making less probable, right? And so there's a whole bunch of algorithms that, you know, attempt to fit that structure. One thing I also want to emphasize is that right now we're fixing these parameters lambda, right? Think of them as confidences that we're assigning to these rules or these constraints. And the big question is that can we actually learn what they are, right? And I'll come back to that point, right? And so how do we fit our model parameters data, right? So let me look at one specific example of this. So one specific example is logical rules. And I know there is a lot of kind of antibodies that's being raised if in the deep learning community if I talk about logical rules, because deep learning people for some reason don't like logical rules, which is true. But let me show you what we're doing here. Suppose I have a supervised learning problem. Suppose I'm trying to solve some kind of a classification task, right? I have some input target space X and Y. And let's say I have some kind of first order logic rules, right? And I have a rule that takes X and Y and spits out a number between 0 and 1. Could be soft number. Lambda here is the confidence level of a particular rule, right? So within the posterior regularization framework, if I have L of those rules, think about on the order of thousands that I can come up with, right? Particularly in the language domain, I can come up with lots of different things that I believe my model should satisfy, right? I can set up this problem, which basically says, you know, if lots of these rules are satisfied, the value of my label should go up, right? The value of the probability under my model should go up, right? So how do we train this model? It turns out that there is a neat algorithm to train this model using knowledge distillation framework. And the knowledge distillation framework is sort of an interesting framework, just a little bit of a background. What you're essentially doing is you're essentially creating something called a teacher and something called a student, which been used quite successfully, particularly in the cases where I have, you know, maybe I have an ensemble of models, and I want to compress that knowledge into a single neural network. And effectively what I'm doing is I'm basically matching soft predictions of this model to the soft predictions of my student model, right? I'm not doing it at the level of the labels. I'm doing it at the level of, you know, pre-activations or at the level of soft predictions, right? And so what are we going to do here? Imagine that I have a deep neural network, and at particular iteration time t, what I do is I optimize my loss, which is what you would do if you were, you know, building a classifier, for example. Yn are the true hard labels. This is a soft prediction coming out of your neural network. So think about ImageNet classification, or whatever your favorite classification task is. So that's a standard supervised learning that we're doing, right? But then what I'm going to do is I'm going to have this auxiliary part where Sn here are going to be soft predictions of the teacher network, right? And so what you're doing is you're essentially looking at the output of your standard model, and you're trying to push it towards soft predictions of the Q network. And this Q network has rules or have constraints embedded into the model, right? And so pictorially, and this is a balancing factor that you have to balance between the two. So pictorially, it looks as such. Imagine that I have label data. I'm building my model. I have my backpropagation algorithm, right? And now I have some constraints or some logical rules, right? And what I want to do is I want to push my predictions of my model to satisfy these constraints, right? Ideally, that's what I want to do. And so to do that, I'm essentially building a teacher network, right, that has these rules embedded into this model. And then you can think of training, so I'm constructing this teacher network with these soft constraints. And I can train a deep neural network to basically emulate the teacher network. So there's this distillation loss. And you can think of just taking this model P, projecting into the Q, and making sure that you're driving these predictions towards this prediction, right? So it's a soft way of incorporating these types of rules. And it turns out, you know, we can train these models. It turns out there is probably there is a way of using even unlabeled data, because this network doesn't require true hard labels. And for things like sentiment classification, named entity recognition, we can actually do quite well when we use this framework. We can also use, you know, on the order, I think that we've been looking, you know, having on the order of like 1,000 different rules that we're incorporating. But one problem with this framework is that what if your rules are wrong? Right? And you're forcing your model to kind of push towards something that might be wrong or might not be supported by the data. And so there is a lot of debate in the community, which is, you know, you have deep learning people that basically saying, we want to learn end-to-end from the data itself. And there are folks that say, no, no, there are constraints that have to be satisfied. But what if these constraints are wrong? And it turns out, you know, what you can do is you can actually learn as you are training these models, you can actually learn the value of these constraints or the value of these confidences. So you can shut down some rules if they're not supported by the data. And in general, you can optimize the parameters of the constraint function. So you can have a function that has certain things that are predefined and certain things that you can learn. And this particular, how we actually update these parameters is a little bit tricky. We typically, what we do is we borrow some connections from reinforcement learning. And so we treat this function f as the reward function that we're basically learning within something called maximum entropy inverse reinforcement learning problems. So there's a way for us to figure out what these parameters should be. And this is what the model does, right? In the case of using these post-conditioned human image generation, again, given different poses, input image, and different poses, you can generate different and this is coming from a deep fashion data set that's out there. And using these constraints, we can get quite good results with fairly simplistic models. We can also do the following task, which is an interesting task. We can do infilling when we're generating text. So for example, imagine that if I give you a template, I want to generate a complete sentence following the template, right? So given a template, I want to generate, and this is a true target, and this is generated, right? And what I want to do is I want to force some of a constraint or matching between infilling content and the generated sentence with the true content, right? So it turns out that this is not a trivial task to do, because in most of the language models, you're sort of generating from left to right and satisfying these constraints by using, you can try to use rejection sampling up until you get the right constraints, but it turns out it's quite difficult to do. But you can actually learn to be able to kind of generate sentences, multiple sentences, by using these constraints. So, and again, you can look at the results. I think in some cases like these models that when you're forcing these constraints, can generate things like I give the movie 7 out of 10, whereas, or the acting is also very good, and as opposed to some baselines typically don't, without constraints, it's very hard to generate something that's plausible, right? So these are two examples of where we can incorporate rules or we can incorporate constraints. Again, these are still quite simple examples, but they do show the promise of constraining essentially the output of your generative model, right? So let me just conclude a little bit, but before concluding, I also wanted to say a few more words about that line of work. So one of the limitations, a lot that I see today in what I've presented and what people are doing in the community as well, is that we're typically only considering very simple forms of domain knowledge, right? We've looked at relational, which is triplets of knowledge graphs, logical rules, simple constraints, right? And if you look at human knowledge, the human knowledge is quite challenging. It's abstract, it's fuzzy, you're typically building on some high-level concepts. For example, dogs have 4 legs, right? If I'm building a generative model of a dog, I want to make sure that whatever I generate has 4 legs, right? Things of that sort. There's been some work that we've been trying to improve object detection algorithm by basically saying, well, if you're detecting something like this and it's a mouse and it has, tail, then it's probably elephant shrew, right? Which is a particular type of an animal. And again, we can do it by sort of propagating that information through the knowledge graphs, right? But still, it's quite difficult at this stage, and the reason why is because knowledge graphs and sort of external knowledge sometimes is very noisy, and it's still quite difficult to incorporate it into deep learning models. One thing, again, I want to emphasize is that one of the key important components in all of this work, I think, is in the work that others are doing, is the fact that you can actually learn these constraints, or you can learn from the data how relevant these constraints are. Because if they're not relevant for your prediction, you shouldn't be using them. If they're relevant for your predictions, you should kind of increase confidence for them, right? And in the last sort of 5 minutes, I wanted to say the following, which is just some food for thought, which is maybe in deep learning, all we need is huge deep learning models with lots of data and lots of compute, right? Maybe that's all we need. How about just, how about like predicting the next word using 40 gigabytes of internet data, right? And this is kind of what was released by OpenAI in the last, I think, last week or so. And if you think about these kinds of models are quite simplistic. You're just predicting the next word given the previous word, and you just scale them up. And that's been the trend in our community, right? Particularly on the industry side, and not as much on trying to incorporate domain knowledge, right? And I think there's still a debate. Do you need domain knowledge, or do you need to incorporate price into these models? Or you can actually take a quite simple model and just scale it up, right? And here's what the model does, which is extremely surprising to me because we work in that space. So what you're seeing here is you're seeing a sentence where you say recycling is good for the world. and you give it the next sentence, no, you could not be more wrong, and then you're saying to the model, okay, just start predicting sequentially the next word given the previous word, and then whatever you've generated the word is, the next word given the previous word, right? So it's extremely simple, kind of a recurrent network, right? And it does things like, it's probably, cherry pick, but nonetheless, it does things like recycling is not good for the world. It's bad for the environment, it's bad for our health, it's bad for our economy. I'm not kidding, recycling is not good for the environment, right? And so it goes through, you can see that it does some form of basic reasoning, right? It says it's not good for the environment, health, and economy. And then it starts talking about environment. It's destructing to the earth, and it's a major contributor to global warming. Recycling is not good for the health. It contributes to obesity and diseases like heart disease and cancer. Recycling is bad for our economy. It increases the cost of a product and in turn the price of everything that's made with that product. Recycling is not good for our nation. We pay a tremendous price for the privilege of having the world's most advanced and efficient recycling system. Recycling is a huge collateral waste of time. And so it goes on kind of, emulating what's going on here. Right, and the reason why I wanted to bring this example is, to showcase also to you that it does some form of reasoning. It's got no knowledge of, linguistic regularities. It seems to capture some kind of long-term dependencies, and it seems to do some form of basic reasoning, right? And so this is a surprising kind of fact because it's a quite simple model, right? There's nothing fancy about specific model that they've trained. They just scaled it up, right? So to me, it was surprising. I think that at some point, obviously, we'll hit the ceiling, but just playing devil's advocate and wanted to show you that perhaps all we need is deep model. And even if, if you look at deep reinforcement learning, there's been some talks on reinforcement learning. You'll hear more on reinforcement learning in the last keynote. But if you look at some examples like StarCraft, right, it's a complex game. You have partially observed environment. You need to build good longer-term strategies. You need to get the right representations. There are multiple players. It may require some form of reasoning, right, to play these complex games. And if you look at AlphaStar, what is this? It's just deep neural network plus some deep RL with bells and whistles. And if you look at Dota 2 type of play, again, it's kind of like a team play. It's just like multi-scale, essentially multi-scale LSTM, right? So there is nothing kind of spectacular, it's just apart from the engineering effort, right? And if you look at, like AlphaStar, each agent was experiencing up to 200 years of real-time play, and it beats the top StarCraft player, right? So again, it was a little bit surprising, and the same thing you see in language, with these examples of BERT and Elmo, these just scaled up versions of Word2Vec that work surprisingly well. So just a food for thought, which is to say, there are two camps in our community that I see. I see camps that basically say we take what we have and we scale it up, and it's almost like having a big hammer, and I'm just going to hammer everything on my way. And it seems like the performance keeps improving, which is a little bit, how do I want to say it? It's great, but it's also a little bit concerning, right? I believe that we're going to hit the ceiling at some point. The question is when, right? And so when we think about, I do this type of research with some of the faculties at CMU, I do believe that at some point we'll hit the ceiling, and I do believe that we'll need to be using some form of domain knowledge, constraints and such on these systems. One of the drawbacks of these end-to-end systems in many cases is that it's very hard to verify the output, right? So for example, when in a domain question answering systems, if I ask you the question and I use sort of external knowledge graph, if I get the answer, I know that this is the correct answer. With deep learning models right now, it's very hard to verify the answers, right? They can give you the answer, but you don't know how good the answer is, and so the verification process is basically it's very hard. But let me stop here and maybe take a few questions.
Thank you.
Thank you.
I'm going to say, this is sort of an inside joke given what you just said. That was a terrific talk, and Russ did an excellent job. Thank you. We will take some questions. If you could line up on the floor. And also, if I could ask, are there any questions? Okay. No questions from the live stream. Go ahead.
Thanks for the great talk. I think, so I'm in NLP research as well, and one of the things that really struck me about the unicorn, basically the recent publication by OpenAI is that the text that's generated is basically kind of this weird cargo culty kind of text generation. It's what you'd expect from like a 10th grader writing a paper who didn't read any of the source material. It's just like, what does somebody writing a paper like this, what do they look like when they write that paper? And I think that for me, that's kind of what you would expect given the nature of the training. It's like you're kind of looking at these like structures and you're like, okay, if I kind of like replicate those structures, then it's going to be believable, or I'm going to replicate that, right? And I really like the direction you're taking it, which is infusing these knowledge structures in, because I think that is a way of getting at something deeper than I've given you the shape of what I think somebody writes when they write on this topic. So,
I totally agree with you. I think that I agree with you, but at the same time, you know, what was surprising to me is that if you asked me 2 years ago, could you generate a coherent, you know, 3-page or like 3 paragraphs, you know, arguing for something or against, I would probably say no. Can you use it using these kind of like simplistic recurrent networks to do that? My answer would be no. Obviously you can't, because previously it was the case that you can generate something, you know, maybe a couple of coherent sentences, and then the model would deviate and talk about something else, and then deviates and talks about something else, and so there's no coherency. You know, syntactically you would see coherency, semantically it would just be nonsense.
yeah.
Right, and the fact that they're getting something that's not nonsense is already kind of intriguing. The question is, you know, what if instead of 40 gigabyte you use 40 terabytes of data, right? Like what happens then? And so I think there is a role for industry here, and only they can do that, and this is great to see where the ceiling is, but I totally agree with you that at some point we'll hit the ceiling, right? Because if I want to generate something coherent, and I need to also have some form of verification, what I'm generating satisfies certain constraints, so that when I go to the customer, it's not just arbitrarily, you know, spitting out something. That's when I think these models will eventually fail. So,
Thanks.
Question on this side?
Yeah, Rose, I think it's a tremendous actually talk here from the medical side. And perhaps I think I'm going to challenge actually your statement about what we need is just more data and just big computer. When you're thinking about, still we don't know how brains works, of course, that basically we don't need so much samples to recognize that the dog has actually 4 legs, right? So I think it's really, I think, a big question about the direction the committee is taking, you know, going through these big things, and whereas actually as a human, we don't need so much things. So just want to get some of your thoughts about that.
yeah, I agree with you. I think there is an aspect of, you know, sample efficiency, right? And in particular domains like medical domains, we don't have the luxury of getting lots and lots of data. That's been, it's hard. So obviously being able to incorporate domain knowledge would just make a lot of sense, because you can learn these systems with fewer samples. So there's a lot of research happening in that space, right? So that's true. Given that, there is also efforts of people collecting more data, right? And if you go and work with, particularly if you look at industry labs, a lot of what they're doing is they just try to collect more and more data, because that's the viable solution right now. I guess we don't have the alternative solution yet, other than just collecting data. You know, I've talked a little bit about, can we incorporate unlabeled data? I think that's an open area of research. But in industry, there is a joke that what do you do with unlabeled data? Well, you send it to the annotation team, right? As much. Of course, you can't label everything, obviously. So we need to innovate. We just haven't managed to do that yet. You know, even with the results that I've shown to you, it is the case that you're using knowledge bases and such. If you have a luxury of having huge knowledge base, which is coherent, then you can really make a difference. And that's what a lot of big companies are doing. If you have a knowledge base which is kind of noisy and incomplete, then you're better off, you know, sticking with unstructured text and tune those systems.
I think we have time for 2 more questions, so we'll take one on that side and one on this side. Go ahead.
So, thank you for this talk. And I think like actually the logical constraints and all the rules, they are important for learning more like an abstract concept or more difficult concept. So my question is like, I want to know how your thoughts on how these like logical rules could be combined. For example, explicitly, like in your teacher-student network, like in the knowledge distillation, or implicitly, like in, for example, the relational reasoning in graph neural networks. So, like, I just want to know some thoughts about
So
it.
the question is, how would you incorporate, for example, logical rules explicitly into
And,
the model so that they're sitting inside the model itself?
Yeah, and also explicitly, like, because as you say that like currently those OpenAI, like the models are simple, but with those large data, maybe they actually the simple model also embeds some simple reasoning or something, maybe that leads to the
Yeah.
coherent result.
So if the question is that if you're using a lot of data, is the model sort of discovering these logical rules on its own? I don't know. I don't have an answer to that question because no one has kind of analyzed what the model is doing, and I think it's very hard to figure out what it's doing. I think a better way of doing things would be kind of the other way around, which is I give you a set of constraints, probably a large set of constraints, and as I do learning from these models, I can actually learn the confidence on these constraints, and I can basically say, you know what, these constraints don't make sense because they don't contribute to my prediction, and these constraints do make sense because they improve my prediction. Ultimately, whatever the task you're trying to solve, that's your measure of how good you're solving a particular task. And if you have a system, what we're trying to do is we're actually trying to learn also what these constraints should be. And if somebody specifies these constraints, but they're not being supported by the data, you want to get rid of them, right? And so I think that's, and then eventually if I specify, set of logical rules and none of them actually make sense for my prediction, I shouldn't be using them, right? And I want the learning algorithm to figure out to ignore those rules, right? I don't want them to be embedded into my system unless there is a reason for it as a hard rule that cannot be violated, right?
Thanks.
Thank you.
Final question over here.
Thank you. Very interesting talk. I'm also interested in a similar topic, but as it applies to learning of scientific knowledge, applying domain knowledge on the scientific system to sort of learn from limited amount of data. How is it possible if you know, for example, that you're trying to model a system, these are the underlying equations, there's the conservation of mass, conservation of energy, that mass cannot become negative. How would you apply those constraints? Would you apply them to sort of your, on the stochastic gradient, and when you're applying the loss gradients, to make sure that the weights do not get to that point? How would you associate the outputs of certain nodes to like actual physical quantities in your system?
So that's a very good question. I don't have a good answer for you. I think that it's an open area research. I don't know if there are a lot of success stories in that space, and that's why I think it's an interesting area to explore. I think that what we've done is we've basically, what you're saying, like the mass cannot be negative, right? That's a constraint that you want to put in your model. So if it generates something, it produces something, it satisfies. So you either somehow explicitly include it into your model as part of the architecture, part of the constraints. Think about like model-based reinforcement learning. I actually have a specific model of how the next state evolves given the previous state and the action that I take, and maybe I can put some physics into it because robots move in a very specific way and there's a physics involved. But it's a good question. I mean, what we're doing right now is we're mostly saying that we're going to try to inject or distill these constraints into the model in a soft way, right? Of course, you can make, if you increase the confidence, it will force the model to kind of have these constraints. So maybe that's one way of doing it. But we're mostly doing it in terms of the distillation. We're forcing our model to kind of just, through the projection, to move into the space where these rules are satisfied, or these constraints are satisfied, essentially, right?
Great. Well, thank you, and another round of applause for Russ, please. And I would like to thank our live stream viewers for being with us here today. For those of you in the room, we have now a 15-minute break. Please be back here at 5 after. We'll get started again. Thanks.